Okay, good morning, Dynamics. Today we're going to talk about vibrations and what causes vibrations and give an example here. What causes a vibration is if you have some situation, maybe like the skyscraper video you just watched. So you just watched this skyscraper that was undergoing a vibration. And what was causing that vibration is there was some initial condition where the top of the skyscraper was displaced off to the right, or perhaps the base, because of an earthquake, was displaced off to the left. But somehow the top compared to the base got shifted a little bit. So maybe the top of the skyscraper was displaced a little bit off to the right. In that circumstance, imagine pulling the top of the skyscraper off to the right. There's going to be some restoring force, some force tending to want to pull the top of the skyscraper back to the left. Okay, a situation like that where if it gets pulled one way or displaced one direction, then there's a force or a moment causing it to be pushed or twisted back the other way is going to tend to cause there to be a vibration. So if you look at the example I have up here with the wheel, imagine taking the wheel and twisting it clockwise a little bit. That's going to cause this spring to be longer, so there's going to be a moment causing it to want to twist back in the counterclockwise direction. And if it overshoots, so if it twists past the original position, that'll cause the spring to be compressed, which will tend to make it push down, causing a moment in the clockwise direction. So we have a situation of this disc on a spring similar to the skyscraper. Okay, now with the disc on the spring, it's going to be a little bit easier for us to analyze exactly how fast it's going to oscillate. With the skyscraper, the calculation would be more complicated, but the overall idea is the same. Okay, so let's look for the disc connected to the spring. If we twist it by some angle theta, the distance that has been displaced, this arc length, will be the radius times that angle. So the change in length of our spring would be that same amount, which would be r times that angle. Okay, let's write out the sum of the moments for the disk. Remember, it's connected to a pin at the center. We'll do the moments calculated about its center of mass, and in which case then the sum of the moments equals I times theta double dot in the k-hat direction. And here we're looking at two-dimensional or planar rotation. Okay, the moment, of course, is the force times the distance to the center. So that would be our spring constant, K, times the displacement of the change in length of the spring, times the radius r, and that equals moment of inertia times theta double dot. Okay, now note though that if the disk rotates in the in the clockwise direction, that actually corresponds to a negative change in the angle. So if I have when I replace the delta x with the r theta, I have to pay attention to the sign here. If I rotate in the negative theta hat, or excuse me, if I rotate with a negative angle, meaning a clockwise change in the angle, then I'm going to get a positive force or a positive moment. So on the other hand, if I have a positive angle, if I rotate with a positive angle, then the spring will get compressed and I'll get a negative force. So this negative sign is important here. Okay, divide both sides by I, and we get some clump of constants, kr squared over I, which I'll just call omega squared, with a minus sign. And this equation right here, we should be able to solve. Okay, so let's just take a moment though to think about it. What we're looking for here is we want a function so that if we take two derivatives, we get the same function. We get back the same function, but with a minus sign. And of course, we can have and maybe a constant out front. Okay, that's fine. Okay, so we need to think of a function that when we take two derivatives, we get the same function back again with a minus sign. So what function makes that? What function does that? So I can think of, well, one very common function is the sines and cosines. Some of you may have also raised your hands and said, hey, how about a complex exponential? Aha, okay, so hold that thought. For right now, though, I'm just going to write this as a sine. Now, of course, it could be sines or cosines. A sine omega t would work, and so would a cosine function. If you take two derivatives, you get the same thing back again. So would like b cosine omega t. Now, note that the omega has to be in there, because when I take two derivatives, the omega would come out twice, giving me an omega squared out front. So I'd strongly encourage you to try that. Take two derivatives of this and see that you get a negative sign times omega squared. So that's two derivatives equals omega squared times a minus sign times what you started with. Okay, and finally, for this particular example, my omega, just comparing this equation and the one above it, my omega has to be equal to the square root of kr squared over I. Okay, finally, so what is the period of this oscillation? Okay, well, to find the period of an oscillation, what you would do is the cosine function or the sine function is going to repeat itself when this thing, it's going to repeat itself the first time when this stuff inside the argument to the cosine function is equal to what? Say it out loud. 2 pi, correct. So when omega t is equal to 2 pi, it's going to repeat itself, and we can use that to solve. So when that stuff equals 2 pi, it will have repeated. So we'll say that I'll replace the lowercase t now with a capital T to represent the period, which is the amount of time it takes to repeat once. So the period of this would be 2 pi divided by omega. Okay, coming up next is adding in some air drag, or adding in some kind of something that's going to make this slow down. What I have right here is an oscillation that's going to unrealistically just bounce back and forth forever. Real world oscillations are actually going to slow down due to some friction or air drag. So we're going to look at that in the, I don't know if I'll get a chance to make a video on it right now, but we'll look at it in class.